Okay. Okay. Good afternoon, everyone. Hope you guys are feeling good today and have good spirit to continue our study in plant utility system. And I'm really sorry. Okay, since last night my house was greatly flooded. Okay, with water. A lot of water. Okay, came from the roof. So behind me, there are several workers who work to fix that issue. So really sorry about that. Okay, so you guys have seen my slide now?
Yes, sir.
Okay, gas turbine. Okay. Eventually, we have entered the 6th chapter in our plant utility system. Okay. Does any of you have the book written by Professor Harry?
Yes, sir.
Okay, so it's in 6th chapter. Okay, and basically my lecture today was just repeating. Sorry, it's just gonna be repeating the book. Okay, anything written in this book. Okay. Okay, so we have entered the gas turbine. Okay, so we have at least 3 instructional purposes. Okay, after you complete this chapter, okay, you are supposed to have at least basic knowledge regarding gas turbine usage in chemical or power industries. Okay, in chemical industries, okay, these days a lot of chemical industries, especially related with energy ones, such as oil refinery, okay, they shift their turbine from the steam turbine one to the gas turbine one. Why? Because gas turbine offers much more responsive systems, and then much smaller place use, okay, and much fewer auxiliary equipment. Okay, it's good. Okay. And the responsiveness of this equipment is significantly better compared to the steam turbine one. Okay, why? Because when you want to increase the load or decrease the load of your steam turbine generator, suppose it's kind of, what can I say, sluggish. Okay, it's not, we are not gonna have quick response. Okay, we need to increase the steam, and then we need to heat the boiler more, put more water first, and then heat up the boiler more, and then what should we do? Okay, check the pressure, and then check the bypass, something like that. I mean, long process, lot of equipments. But for the gas turbine, okay, we just really need to change the revolution. Okay, the rotation per minute. Okay, it can be changed, simple. Okay, so, but it's not the best. I mean, for any equipment in chemical plant, there is no best equipment for any type of chemical. I mean, for all type of chemical plant. Okay, there is no silver bullets for every issues, in our chemical industry. No. I mean, it's good, it's better for special case, something like that. Okay, when you are working with when you are working with steady state chemical plant, and then large amount of power use, steam turbine offers better option. Okay, but when you are working in quite limited area of chemical plant, okay, gas turbine always gives better option. Okay, so in plant utility system, we never want you to be indoctrinated. Okay, it's not a dogmatic approach. Unlike in chemical reaction engineering, suppose PFR is always better at the end, at the reaction order higher than 0. Okay, no, for plant utility system, there are case by case, okay, approach. Okay, you cannot just simply use everything. This one is the best, and then we will use it. Okay, no, nothing like that. Okay, but at least you need to know why gas turbine is used. Okay, and then second purpose of this chapter is to increase your capability to calculate energy usage in usage or maybe produce here. Okay, in typical gas turbine. Energy involved. I'm sorry, here should be energy involved. Okay, involved. Okay, you need to know it from the basic. Okay, and maybe I'm gonna repeat a little bit discussion or chapter from the thermodynamics class. Okay, and then third one is we want to know better. Okay, regarding the gas turbine operation and its auxiliary equipments. Okay, even though it's claimed that gas turbine has smaller space, okay, occupies smaller space, has fewer auxiliary equipments, but still it needs some auxiliary equipment. Okay. Okay, so this is a typical gas turbine. Okay. Wait a minute. For this class, I'm gonna share a document through the chat room. Okay, after some slides. Okay. Okay. So this is the gas turbine. Okay. Gas turbine. So when we are using gas turbine, okay, the process is always started with sucking the air. Okay. And then after it's being sucked, then it's being compressed. Okay, compressor. Okay, so after being compressed, we combust it or we burn. Okay, then exhaust is there. And as you can see here, what is this? It's called coaxial. What does it mean? When you see coaxial, means compressor and turbine has same axis. Okay, has same place, and they have same rotation per minute. Okay, and the one in fact, okay, the one that rotate the compressor in gas turbine is not the external energy, unlike in Rankine cycle. Okay, when you want to compress the water, okay, from 1 bar becoming suppose 40 bar, you are using what? Pump here. Okay, and this pump is powered by external energy source such as electricity, steam itself, or diesel, and other things. Okay, but for gas turbine, it's unique. Okay, for the gas turbine, the one that rotates the compressor is the turbine. Okay, that's it. Okay, so why is it acceptable in a chemical plant? Okay, it has high durability and versatility. So why it's high? Why does it have high durability? Usually, gas turbine was designed for aviation purpose. So most likely, okay, most likely the material involved in gas turbine is the strong ones. Okay, we don't put aluminum in there. Okay, simple aluminum, no, it will melt. Okay, in fact, material used in gas turbine is much more expensive compared to the steam turbine one. Okay, so when you are designing a chemical plant, so always two aspects here. I always, yeah. Here is OPEX, and the other one is CAPEX. You know OPEX and CAPEX? OPEX means operational expenditure, and the one in CAPEX is capital expenditure. For gas turbine, okay, in some cases it has very low OPEX, but still, okay, it has very high CAPEX compared to the steam turbine ones. Why? Because the material and rotation, okay, rotation is very high, 1,000 of rotation, 1,000 RPM, 10 of 1,000 of RPM. And it has to withstand very high temperature instead of steam. So when you did your steam calculation, maybe when you have degree of saturation, maybe 100 degrees Celsius, okay, it's not at the 40 bar, maybe the temperature is maybe around 300 or 350 degrees centigrade, okay. But for the gas turbine, especially the turbine, okay, the combustion and turbine, it has to withstand the combustion temperature, maybe 800 till 100, 200, 1200 degrees centigrade, around those temperatures. And you can imagine what's the difference. I mean, the material used in steam turbine will not withstand, okay? It won't withstand the environment used in the gas turbine. That's why it's already durable by itself, okay? Because the material is expensive, okay, it's durable. So that's the seesaw effect, that the trade-off, okay? It's durable, but it's expensive. And second one is versatile, okay? Okay, versatile. Why? Gas turbine fuel, here is fuel, okay, can be changed. But there is a limit in it, but it can be changed, okay. Suppose yesterday you use kerosene. You know kerosene? You know kerosene? What is the expression kerosene?
Yes, sir. It's one of the fuel.
See the 14 from this, okay. And today you use this up, okay. Then you change to the gasoline one. C8 till C10. It's still working, but you need to, you just need to drain the old fuel. What else? Diesel fuel, C14 till C16. It also works. Okay, that's versatile one. Okay, but we must fulfill the requirement that the fuels should be able to be nebulized. You know, nebulized. It should be nebulized. Okay. So we don't want to use any solid fuel in here. So you don't use coal. Okay, coal is not good. It's bad. Okay, but any liquid fuel, so even you change it into LPG. You know LPG. Maybe here C3, C4, it's still working, but still with different efficiency, but still works. Okay, that's why U.S. Army, you know U.S. Army, Marine, and U.S. Force, the Armed Force, they use gas turbine in their tanks. M1 Abrams use gas turbine, okay, instead of diesel. Okay, when so you can imagine, okay, the versatility of gas turbine. When I read from the magazine, okay, they said that this tank can can change the fuel, okay, as it wishes, okay, from day to day, okay. Maybe today the diesel fuel is empty, they just need to drain the diesel fuel and change to the gasoline. Suppose their gasoline is empty, okay, because it's a war, okay. Not every logistic can be fulfilled, okay. So they can change to the kerosene or the after, okay, aviation turbine, something like that. Aviation fuel is okay for their tanks. So it's, you can imagine its versatility. Okay, only different efficiency will be reached. Okay, for different fuel. Okay, and then it requires relatively fewer auxiliary equipment compared to the steam turbine. Okay, the most compact, okay, is of course the diesel. Okay, the diesel one, you know, the diesel engine. Okay, is very compact, but the diesel piston engine, its fuel, yeah, the diesel piston engine fuel cannot be changed as we wish. Okay, because the compression ratio will be greatly affected by the fuel type. Okay, even when we change from the conventional diesel fuel, okay, to the biodiesel, okay, sometimes, okay, it create bad impacts to the machine. Okay, yeah, that's why we mix. Why? Because different compression ratio, different properties can really affect the diesel engine, but for this one it's quite good. Okay, sorry, here pressure. Okay, but when we are comparing it to the steam, okay, for compared to the Rankine cycle, so if you still remember how many equipments at least exist in the Rankine cycle, first is what? The turbine itself. Okay, second one is condenser. Okay, maybe here we are using cooling tower. You still remember this, don't you? And then, sorry, third is one, pump. Then fourth is boiler. Okay, in boiler itself, it has its own auxiliary. Okay, feeding system, and then reboiler, or many things. Okay, many valves in there. And the pump itself must be powered by other power sources. And for the turbine itself, yes, turbine is turbine. Okay, and then condenser, you can see that the working fluid is lost in the condenser or cooling tower. You still remember this, don't you? Okay, you still remember this, I believe. Okay, but now you imagine these four equipment, okay, occupy a lot of spaces. Okay, because the boiler itself is big, it's huge. Okay, then what? The pump may be small, but the turbine is going to be big, it's huge, including its safety system, the regenerator, something like that. Okay, and then the cooling tower. Is it small? No, it's big, really big compared to the engine itself. It's quite big, it's high. Okay, stall, and then it occupies many spaces. But for gas turbine, okay, we just use smaller, so it's like an engine. Okay, small. Okay. And the third one, it has faster response during operation. Okay, like I said to you before, when we want to when we want to what when we have the suppose this one is the boiler and this one is the turbine. Okay, here is the boiler feed water, and here is the fuel, and this turbine is maybe here something electricity in there. When you want to increase the electricity, okay, what do we do at the steam turbine generator? Usually we need to increase the heat. How do we increase the heat? We need to increase the fuel. How do we increase the fuel? We open the fuel. We open the fuel valve, and then we also open the air register in there. So lot of things happen. The gas turbine, simple, really simple. Okay, just increase the RPM. Okay, because it's on purpose. It's engine. It itself is an engine. Okay, so yeah, many thermodynamic process happens in a much smaller space. Okay. 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 So let's talk about the history a little bit, okay? Because when I give you a direct maybe a direct approach, it's gonna be sleepy. Okay, so very first thing was the machine around 150 BC. Okay, the Egyptian. Okay, they used this steam machine. I forgot its name, but somehow they boil. Yeah, they boil by using charcoal here, and then steam, something like this. And then when this system is combined with this one, okay, around 1280, okay, yeah, we know the Chinese fire arrows, okay, and then around 1580, Da Vinci, okay, designed this one, okay, maybe never experimented in physics, and then 1790, okay, I forgot his name, it's from Germany. So he designed kind of heat engine in here, and then same 1872. So this system was well developed in Germany. Seriously, these people really smart. Okay? 1872. They I forgot the name, but very first design of gas turbine engine exists in there, and then 1903, 1918, this one is for the aviation derivative, and then 1930s, okay, and you can see here it's not airplane from United States, it's always airplane from Germany, it's Henkel. Okay, so the gas turbine, okay, gas turbine was initially developed for transportation. Okay, since it's fast, okay, it's fast and it's powerful and it's hot. Okay, nobody wanted to design anything that moves on the land. Okay, using gas turbine, so either in air or on the sea. Okay, but it's good. 1930s. So when you learn the history, okay, when you learn the history, Germany, okay, at the time use jet airplane first, okay, mission jet airplane compared to the Allied. Okay, so so 1940s was World War II, I believe. Okay, so I'm gonna touch this one. Basic concept of heat engine, or basic concept of any engine, was in any type of machinery, energy was extracted or generated by utilizing potential difference. Okay, when you still remember, when you have the usual water turbine, okay, here we want to extract the energy. Okay, here is the potential energy, and then the downside is the kinetic energy. Okay, and always energy always flows from the higher potential to the lower one, and we always want to put a turbine in there. Okay, we want to put some kind of engine in there so that we can get a rotation work or some peristaltic work. I mean, we want to utilize that. Okay, for the water turbine, okay, what do? We build a dam. Okay, we build water duct. We build dam. Okay, we dump something like this. Okay, and then you put turbine in here. Okay. But what happens if we have engine in here? Okay. Wait a minute. Okay, sorry for the disturbance. Okay, we always want to have to utilize this flow of energy. Okay, but what happens if you want to utilize it in heat engine? Okay, for any of heat engine, this point is related to the highest enthalpy of working fluid, and this point is always related to the lowest enthalpy possible of the working fluid. When you still remember, okay, the steam turbine, we have here H3, here H4. You still remember this one? Okay. So in this place, okay, H3 is always bigger than H4. Okay, then we extract work from here. Any engine, any machinery, it's always like that. Okay, we extract the energy from the delta enthalpy, always like that. Okay, and then what the main questions are: how to extract the energy? What kind of working machinery should be installed there? And then how to manipulate the working fluid so that it can reach highest enthalpy condition. That's why for the steam, okay, steam turbine, what should we do? Okay, here suppose we pump it, then what should we do? Here this is the boiler, okay, so that it changes. Okay, maybe here we have H2, here we have H3, and here is liquid, here is what? Vapor. Okay, as you can remember, maybe the H of vapor is much bigger than H of liquid. Okay, and by maybe H of, when we have because the H, the enthalpy, is the function of P and T, okay, for any fluids. Okay, when you have H of 80 bar and you want, and the outside, okay, the outside of the turbine maybe is 10 bar, and here is delta H, and here is the work extracted. Okay, and how to reach this one? Many things must be done. Okay, can be heated, okay, can be mixed with fuel, then combusted, something like that. Okay, and the third question is, what type of working fluid should be used? Okay, because like I said to you before, we need to optimize our needs. Okay, you guys still remember refrigeration cycle? Anyone of you still remember that refrigeration cycle? It's not heat engine, but it's heat pump. You still remember that?
I think so, sir.
Okay, so for refrigeration, why do we choose R134? Suppose, why don't we choose water? You still remember that?
Is it because of the heat capacity or something, if I'm not mistaken?
Yeah, anything. I mean, when you see the pH diagram, okay, PV diagram or TS diagram, okay. When we use water here, from this one to this point, we need very high pressure to so we can when we for refrigeration, the evaporator is always using what this one, GT valve, so the expansion is isenthalpy, okay. And for water, since the default is the non-compressible fluid, when we expand it in isenthalpy mode, okay, isenthalpy with same enthalpy, it just does not absorb heat too much, okay. But maybe it's when we are using CFC, chlorofluorocarbon, okay, R134 suppose, okay, it can, when we expand it using isenthalpy mode, okay, in a GT valve, okay, it can absorb the heat very much. That's why in here my point is we need to choose the right fluids in there, okay. We need to choose the right fluid, okay. But and for your information, I have ever attended a seminar from professor from Japan when I was taking my graduate course. He said that he could create water as the refrigerant using very high, very high efficiency of compressor. So it's quite difficult, but yeah, but still, he said that not 5 degrees Celsius is the lowest temperature when water is used as the refrigeration agent, okay, refrigerant. Okay, here, when we need, okay, later on, you will also study the diesel cycle, Otto cycle, maybe a little bit, maybe, okay, diesel cycle, maybe. The working fluid is what? Air. Okay. For Rankine, working fluid is water, okay? Water. But for Brayton cycle, diesel cycle, the working fluid is air. Why? Because it's abundant in there, and then, yeah, it's abundant, okay? Okay. And please be careful when we are talking about Brayton and diesel and Otto, internal combustion engine, something like that. The working fluid is always assumed as air, even though in there you have CXHY combustion with air to create CO2 plus H2O. Okay, this process is there because we want to do this. Okay, and usually, okay, I'm not sure, but usually the volume, okay, V of hydrocarbon or fuel compared to the V of the air is quite non-significant. Okay, maybe 5%, something like that. I'm not sure because I just know it through the theory. I never calculated by myself. Okay, my field is catalysis, okay, so not there. But at least this one is less than 10%. Okay, less than 10%. So any properties regarding our working fuel is always assumed as the air properties. Okay. So this one is the ideal Brayton cycle. Okay. Even though in here it's called the internal combustion engine. Okay, ICE. Okay. Rankine is external combustion engine because the combustion happens at the boiler and outside the turbine. But for the Rankine, it's internal, it's inside the turbine. Okay, so the process is always started with what? Okay, isentropic. So this one is the ideal. So isentropic compression of air. Okay, the air is compressed isentropic. Okay, flexible adiabatic. Okay, and then heat by what? By mixing it with some fuel, and then this fuel is going to be ignited, combusted. Okay, and then expansion. Here is compression, here is heating, here is expansion. Okay, when you are working with the heat engine, don't depend yourself too much with PV diagram. PV diagram is really quite difficult to understand for this system. Okay, I really like the TS diagram, but that's only my personal preference. Okay, wait. Okay, so please remember, when the expansion or compression involving any moving parts is always assumed isentropic at the ideal condition. Okay, it's always assumed as isentropic. But when the expansion happens without using moving part, okay, suppose the expansion happens at the valve, GT valve or pressure reducing valve, okay, it's always assumed as isenthalpic. Okay, so expansion or compression, okay, compression cannot be done with the valve, but expansion, okay, expansion, okay, if you see something like this, this always has anything to do with tropic, okay, so it's isentropic or polytropic. Okay, but if you don't see any that symbol, instead you are seeing this valve is always isenthalpic. Okay, memorize this one seriously. Okay, so at the end of this of your study in our chemical engineering department, you don't need to study thermodynamics, okay, because thermodynamic cycle is always related to those two things. Okay, but for the compression is always isentropic. Okay, assume as isentropic. Okay, and the non-ideal one is always polytropic. Okay, you still remember this one, don't you? Anything with moving equipment is always tropic. Okay, either polytropic, isentropic is there. But anything with non-moving equipment, such as the pressure reducing valve or Joule-Thomson valve, is always related to the enthalpy. Okay, isenthalpy. Okay, okay. You remember that?
Yes, sir.
Okay. So that's the easiest part. Okay, just remember that. Okay, it's not complicated at all. Chemical engineering is an easy stuff. Okay, sometimes we ourselves create more complication in our job. Okay, so only this one. And please remember another thing. Okay, when you have ICE, internal combustion engine, okay, the working fluid is always assumed as air. Okay, don't talk about, so the working fluid is what? Is air, CO2, and the hydrocarbon? No, no, it's big. No, even though sounds like more detailed, but so it's wrong. Okay, okay. The working fluid in this case is air. Okay, you remember this one? Okay, any diesel cycle, Otto cycle, Brayton cycle, internal combustion engine cycle, the working fluid is air. Remember that? Air, not other fluid. Okay. Okay. Okay.
Sir,
Yes.
why does it have to be air, sir, and not others?
Yes.
Why does it have to be air and not others, sir?
What do you mean? You can just imagine for the Rankine. Is it air? It's water, isn't it?
Rankine is water, sir.
Yes.
But for like Brayton, Otto, and diesel, the one that you said, sir, why does it have to be air, sir?
Yes, because like I said to you before, okay, in this part, okay, it's only used to increase the enthalpy. It's 2 to become 3, and then the volume of the fuel is much smaller than volume of the air. You can you imagine that? In car is called carburetor. That's the mixture of the air and the fuel, nebulized fuel. It's always much smaller. Okay. Okay.
Yes, sir.
Okay. Because it's much smaller. I want actually it's not only air. Okay. Because in here, okay, here will be O2, nitrogen, CO2, and CO possibly. Okay. All together, they are going to push the turbine, but only these two are regarded because it's really small. Okay, if this one is getting big and bigger, maybe becoming 5%, 10%, then you need to change your engine. Okay, okay, because it's not efficient anymore. Okay, even though okay, I will talk about the efficiency later. Okay, maybe tomorrow. Okay, for the real efficiency. Okay, this compressor, turbine, and yeah, this one. Okay, so the question is, when we always have lower what can I say, low efficiency, okay, why do we still use engine? Because this engine, okay, why do we still use it? Because this engine is enabling us to change the energy, okay, from the chemical energy, okay, if you still remember this one, from the fuel in the form of HHP, becoming what? In the form of kilowatt of shaft power, maybe horsepower, okay, brake horsepower or fluid horsepower, okay. Why do we still use it? Because it enables this conversion, okay, okay. Instead of just heating it, okay, you cannot move anything by burning your fuel, okay, without any engine. No, you cannot. No. Okay. Okay. So this is the HSP becoming kilowatt. That's it. Okay. So I believe you have studied this in your thermodynamic class, haven't you? About the breakdown.
Yes, sir.
Okay. So prior to this class, okay, do you have any different understanding with me? Prior to this?
No, sir. Maybe just not in detail. Maybe I just forgot, sir.
Yeah. Okay. Yeah, that's students everywhere is like that. But at least I want to imprint, okay, imprint this memory to to your sense, okay. When you are working with internal combustion engine, okay, your purpose is to change the energy from the chemical energy, okay, to become work, okay, shaft work, okay, maybe horsepower, something, movement, kinetic energy or something. We call it as what can I say? Brake horsepower, shaft horsepower, something like. I mean, to the kinetic energy, okay. So we want to change that. That's why we use this one, okay. So since the time is 8:46, I'm gonna stop till this slide, okay? Then tomorrow we will do more calculation. Since the 3:35, we use more calculation. I hope you are not gonna sleep tomorrow, okay? Okay, so this is the component of gas turbine. So we have air compressor, unlike Rankine cycle. Compression work considerably affects overall cycle efficiency in gas turbine engine. Yeah, because it is a coaxial, and you can see here, if you want to, okay, sorry. Okay, when you increase the pressure, okay, maybe this is the liquid, this is the gas, okay, you want to have P1 maybe 1 bar, and then P2 here 10 bar, and this work is work 1, and this one is work 2, okay. In any application of compression, okay, work 2 is always much bigger than work 1. So it's more difficult to compress compressible fluid, seriously. Yeah. Okay. It's more difficult to compress compressible fluid. Okay. Energy involved in there is much bigger. Compressor or pump, okay. That's why when, like, maybe not to you, to the regular class, okay, when you still remember at the Rankine cycle, okay, you still remember at the Rankine cycle. So here is the boiler with water, then here is pumping, then here is boiler. Why is it like this? Why don't we just put it like boiler with water, boiler, and then compression here? Sorry. Why it's not like this? Because you can calculate it by using enthalpy at the steam table, okay. This is option number 2, this is option number 1, okay. At the option number 1, energy used, okay, to compress boiler feed water from 1 bar to become 40 bars, suppose, it's much smaller, okay, compared to case number 2. Increasing the pressure of the steam from 1 bar to become 40 bar is much more difficult, okay. Okay, so this is it. And you, as you can see, in any of the cycle, the increase of the pressure is always happens prior to the working fluid heating. Okay, you can still imagine here in the Rankine cycle, okay, in the Rankine cycle, the pressure of the water is being increased first instead of being heated. And in here, okay, in here, okay, in here, we always increase the pressure of the air first instead of burning, okay. That's kind of rule of thumb. So, and you will see at the diesel engine, okay, at the diesel engine, okay, this combustion always happens after the compression, okay? Because increasing, because it's kind of has no use, okay. When we combust it first, then increase the pressure, it's no use, okay. We always want to increase the pressure first, okay. Okay, tomorrow we will draw many things in here. I hope I'm gonna share it through Pak Wawan, okay? This slide, and then tomorrow I want you to prepare it in your PowerPoint, okay? So we can draw something like this, okay, okay? So I want you to feel it by yourself, okay? Drawing the ideal Brayton cycle, and then actually possibly, okay, the probability of you using this drawing skill, maybe less than 50% or 20% at most. You're not going to meet this in your job, possibly, unless your job is going to be a lecturer or some sort of researcher like me. Okay, when you are working in the chemical plant, nobody wants to draw the thermodynamic cycle. Okay, nobody wants to draw it. Okay, but it's important. Why? Because you know the map of energy involved in your heat engine. Okay, okay? Let's see tomorrow. I want you to draw it by using PowerPoint. Okay, then I'm gonna make a quiz for you. Okay, because your plant utility system is always identical with quiz. Okay, it is for the regular class. Okay, how many quizzes have you experienced from Pak Wawan or Pak Walmiki or maybe Pak Hendra?
One, sir.
One, two,
Eh,
Did
two?
Yeah, one before the UM1 and one before the UM2.
See, in regular class, we have already had 12 quiz. That's how we train it, okay? I really agree with Pak Harry method to train it, because when we don't have clear picture, okay, when I just suppose giving you this and this, okay, I believe in less than 1 month after the exam, you will forget it. Okay, you will forget it, and I am gonna be very sad. Okay, so I want you to download it through Pak Wawan later on. Okay, and let's draw it together tomorrow. Okay, then I'm gonna make it as quiz. Okay, I hope you are not gonna be burdened with this one. I hope you can learn with me, because plant utility system is actually thermodynamic too, mass and heat balance too. Okay, it's like a combine of many classes. Okay, and at the end you will learn electricity. Okay, it's much more boring if you don't have quiz. Okay, and for your information, quiz is not gonna take very big portion, but we really require you to do what we say. Okay, so that at the end you will train. Okay, and please, after the quiz, always do good archive. Okay, never throw away your document. So maybe at 10 years, maybe 5 years later, you will still be able to find it. Okay, okay, I want to stop it for today. Okay,